We now start our discussion on sound. And to start, we talk about what sound is, right? How sound is produced. So the first thing to note is that sound is a longitudinal wave. So recall what this means. Typical transverse waves, right, are you have a wave propagating, but the motion of individual particles uh, is perpendicular, in this case, what we would say up down, is perpendicular to the velocity of the wave. So if my wave is traveling to the right, whatever our wave is, I don't know, we'll label it K, right? So K would represent a transverse wave where individual particles are traveling up and down, but the wave itself is traveling forward. So this is your guitar string type wave, right? But sound is longitudinal. So what that means is that the sound, the wave itself makes your particles oscillate back and forth as the wave moves forward. Okay? So, in a typical speaker, right, this is the quintessential way to produce sound. We'll talk about your vocal cords here in a moment, but the way that sound is produced by a speaker, whatever source is producing the sound, be it a CD player or a car stereo or whatever, you have a signal that is sent to the speaker, and the magnets in the speaker correlate with the circuitry from the signal device to cause the cone to move back and forth. The cone pumps. And if you actually have a very low frequency tone, you can actually see a speaker move back and forth. Okay? So your speaker is moving back and forth. And what this does is it pushes the air immediately surrounding the speaker. And as it pushes on the air and it's moving back and forth, it causes these regions of high pressure and regions of low pressure. And if you think about it, this should make some sense. Suppose I have some air in a tube, okay? But I have a piston, some sort of plunger, okay? So my container is filled with air. And if I immediately pull this plunger back, okay, if I immediately pull the plunger back, instantaneously the molecules won't have time to respond to the increased volume. And so, for just a brief instant, the molecules are essentially where they were. And you have this region of low pressure compared to the rest of the pressure of the fluid or your gas, whatever the case may be. And so, as the cone in your speaker moves backward, it creates this region of low pressure. And then, as the gas can respond to it, it then flows toward the plunger. But then, if we are thinking of the plunger as the speaker cone, then when the speaker cone pushes forward, it compresses the molecules immediately in that region. and gives them a much higher density than the rest of the molecules that were dispersed throughout. So then you have a region of high pressure. Okay. And if this process just continues at a constant rate, you're just pulling the plunger back and pushing it forward, then you just get these regions of high compression of your air molecules, and then low compression, and then high compression, and low compression, and high compression, and low compression, and so on. And this pattern moves through the medium with some speed v, and in this case that would be the speed of sound. Okay, so we call these regions, the regions of high pressure we call compressions, and the regions of low pressure we call rarefactions. Okay. So as this wave of pressure is propagating through the air, this is sound. Now, there's an alternative way of looking at this. Instead of looking at the pressure, you can look at the actual displacement of individual air molecules, right? And so because this is now displacement, we give this the symbol S. Okay, but you'll notice, right, if you look at, think about these two diagrams right here, your regions of low pressure and your high pressure occur before your molecules actually start moving. And so what that means is your pressure wave, if we think of this as a sine function, right? So high pressure, low pressure, high pressure, low pressure, high pressure, low pressure. If this is a sine function, and I'm going to drop the phase constant for the moment. The phase constant just dictates when we start our stopwatch. Then because these regions of high pressure and low pressure don't necessarily mean the molecules have actually started to be displaced that much yet, that means that your displacement curve is going to be out of phase with your pressure curve. And so if P is a sine function, then that means S is going to be a cosine function, because these will be 90 degrees out of phase. Okay, so if you actually want to look at the position of individual molecules, then we would use this cosine function. Okay, now it in truth doesn't matter which one is which. You could label the pressure wave as a cosine function and the displacement as a sine function. The only thing is what their phase difference would be, whatever that phase constant phi would be. But they will always be out of phase by 90 degrees to one another. Okay, so that's the main point to drive home. And so if you hear a constant tone with your speaker, then you produce a steady sine wave. So when you're producing a constant tone, your speaker is just bouncing back and forth at a constant rate, causing these compressions and rarefactions at constant positions from each other, and that produces your sine wave. And the thing to note is that this sound will move out in all directions. Okay? And so this pressure wave is going to move essentially spherically outward from your speaker. I don't really think that I have the artistic skills to draw that, but you can think of this if we have a speaker okay, then the sound coming out of this is going to come out in spherical shells surrounding it. And as these shells expand, their surface area is going to increase. And as we will see in just a moment, because the surface area is increasing, that means the intensity is going to decrease. And what we perceive as intensity is volume. Okay? What our ears perceive as intensity is volume. But so sound at its root level is just these compressions and rarefactions moving through the air and interacting with your ear. So your ear is actually a pressure gauge. Which is why, if you've ever been on a flight and felt lightheaded or lost your balance, or experienced an extreme and rapid elevation adjustment, like maybe, say, driving up in the mountains, going up a steep road and it's, one pressure at the bottom and then it's a higher pressure at the top, and your body hasn't had a whole lot of time to adjust. Your body responds to that, and so that's one reason why you can get vertigo when you experience rapid elevation changes. But the bottom line is that sound is this longitudinal wave that is created by the compression and rarefaction of air. Now, when you speak, okay, you don't have a speaker cone, obviously, in your throat, but you have vocal cords. And instead of a speaker cone vibrating back and forth, your vocal cords are vibrating back and forth, okay? Now, when you hear a complex piece of music through a speaker, you don't just have this constant tone. You will have a superposition of lots of signals moving through the speaker. Okay, so your speaker is going to move in a very, very complex way, if that's the case. All right. So I don't think we have to say too much more about that. We will talk about this maximum pressure term here in just a moment. Okay. But I think that's all we need to say about it. Let me do say a little something. Your maximum pressure change. Okay, so this isn't the maximum pressure. This is the maximum pressure differential between your high pressure and lower pressure regions. So the maximum change between these two is the amplitude of your pressure wave. Okay, and it is true that the higher the amplitude of your pressure wave, the higher the amplitude of your displacement wave, right? And so, I think that that's all we need to say about that. So, speed of sound in air. Okay, the speed of sound in air has been modeled by this equation, and this equation models it very, very well. Okay, so you'll notice that the speed of sound in air is temperature dependent. Okay, so if you look at this, the colder your air is, the slower the speed will be. The higher temperatures will be higher speed of sound. And I really should have included the units here. This is 331 meters per second. Okay, so if you know what your temperature in Celsius is, then you can use this formula to get the speed of sound in air. Now, this formula is assuming atmospheric pressure, okay? but it doesn't change all that much from sea level up to 10,000 feet. Okay, it doesn't change really all that much. So for our purposes, we can consider this to be pressure independent. Um, you will often see this number for the speed of sound in air. Okay, um, and where this comes from is we usually take 20 degrees Celsius as our standard temp. And if I plug in 20 degrees into this formula, okay, then this is 342.9. And for most cases, we just round that up to 343. Okay, so 331 is obviously the speed of sound you would get for 0 degrees Celsius, or at the freezing point of water, right? So when my air is at 331, or I'm sorry, when my air is at 0 degrees Celsius, my speed of sound will be 331 meters per second. So increasing by 20 degrees actually does have a very appreciable difference, right? Um, so let's see. It differs by roughly 12 meters per second. And let's just do a percent difference on that. Yeah, 3.6%. So increasing the air temperature by 20 degrees Celsius increases the speed of sound by 3.6%. Okay, so it's slight, but it is appreciable. Now, of course, air is not the only thing that sound can move through. Sound can move through almost any physical medium. Okay, so the speed of sound, the general formula for the speed of sound is an elastic property divided by an inertial property. And so your elastic property is defined as essentially how does your property respond, or how does your medium respond to deformation. Okay, if I apply forces in different directions and those forces are imbalanced, how does my property respond elastically, right? Does it stretch? How does it stretch? How does it compress? How does it respond to shearing forces and those kinds of things? Your inertial property is just your a property in any case regarding the substance itself. And in the cases of fluids and sound, your inertial property is density. So this is just a property of the material itself that is inherent about it, regardless of external things like external forces. Okay, so for fluids, we have what we call the bulk modulus. And your bulk modulus is essentially how does a volume of fluid deform under unbalanced forces. Okay. For I wrote sound. This is solids. Okay. For solids, we have what we call the Young's modulus. And your Young's modulus is essentially how does my material stretch as it is put under tension. Okay, that's the most common way that Young's modulus is measured. How does my material stretch as it's put under tension? Okay, so that property, what we call stress over strain, if you will, divided by density, the square root, gives you the speed of sound in solids. And then for ideal gases, this formula is a little bit funky because we haven't covered some of the things in here, but gamma is your what's called the gas constant, adiabatic gas constant. And for ideal gases, this is usually 5/3. R is your what we call the well, this is the gas constant. Um, and M is the molar mass. And I guess for completeness, TK is your temperature of your gas in Kelvin. Okay. Um, sorry. Your gas constant R, for completeness sake, has the value of 8.31 joules per mole, joules per mole times Kelvin. Okay, and this R, there's two ways. Well, there's multiple ways, but your ideal gas law is usually written something like this or like this. And these are equivalent. Physicists often like the top, and chemists often like the bottom, but in any case, R here is the gas constant that appears in the traditional chemistry form of the ideal gas law. We're not really going to go into detail with this equation as it's written in these two forms, because we will in the future chapter on thermodynamics when we get to thermodynamics. Okay, but just know that for general materials, if you have a fluid, if you know what the bulk modulus is, how how a volume of your fluid would deform under differential forces divided by the density of that fluid. And if you think about it, that should make some sense, right? Because sound waves are pressure waves, these rarefactions and compressions, and these are deforming the air. And so it would make sense that the speed of sound in gas, fluid, which you can consider air to be a fluid, is equal to how the air is deforming under these unbalanced forces divided by the density, right? And what's unbalanced about the forces, right? Well, remember that pressure is equal to force per unit area. And so if I have a delta P over a given area, if we're not letting our area change, then that means I have to have a difference in forces, right? So you will have these forces not be balanced. You'll have a delta F acting over some surface area of your material, and if your forces are unbalanced, then you get this differential in pressure. And when you get that differential in pressure, then you get the waves that we were discussing just a moment ago, right? Your compression rarefaction sine wave here, okay? All right, so sound intensity. So this is what our ear perceives as loudness. Okay? The intensity of a sound is what we perceive as loudness. And the basic idea of intensity is that intensity is equal to the power in a spherical shell. So this is where this whole expanding spherical shell idea comes in. The power in that spherical shell divided by the area of that spherical shell. Okay. And so, what we can say is that the intensity at a given position, R, away from some source. So, let's say I have like a siren, right? And it's blaring out sound waves. Well, these are propagating away in these spherical shells. Okay? And the surface area of a spherical shell, let's look at this largest spherical shell here. So we'll label this as R. So the power is going to be constant, right? Your power is constant. And what we mean by that is, if let's suppose this is a siren generating a constant tone, then the total amount of energy in this inner sphere has to have the same total amount of energy as this other sphere, as all of the other spheres that are expanding away from the siren. So the power is the energy produced by the sound per unit time. Okay. So for a given object, this is going to be a constant power. Now, this is not necessarily true once you get into varying sounds, right? Obviously, when you talk, your voice goes up and down, your inflection, your loudness increases at some points, and then it decreases at others. And so, when you have a situation like that where your sound is variable, your power is not necessarily going to be the same. But for an object that is producing a constant tone, it will be. Okay? And so what that means is, and this is just energy conservation, right? This is just energy conservation saying that the energy produced by this source has to be the same per unit time unless something about the source changes. And that's the argument that we make to say that P is going to be constant. But you'll notice that the surface area is 4 pi r squared, so this is an inverse square law. Okay, so what that means is, let's now label this as R2, and let's label R1 as a smaller sphere. Okay, so under the condition, let's say that R2 is twice as large as R1. How does the intensity of object 2 compare to object 1, right? Well, if we calculate the intensity of I1, we have the power produced by the sound divided by 4 pi R1 squared. And if I look at I2, this is equal to power divided by 4 pi R2 squared, but this is equal to the power divided by 4 pi twice R1 squared. So this is 1/4 the power divided by 4 pi R1 squared. So very similar to gravity, if I go twice as far away from a source, I have 1/4 the intensity. In gravity, it was 1/4 the force, right? So that is how intensities are related to each other, right? This is an inverse square law. However, if your source is variable, like a siren, typical sirens, right? They go up and down and so on. What we typically will talk about the intensity of these sources will be the time average of the power divided by the area. Okay. Now, we're not going to go through complex calculations with this because this is decently heady, but just know that that is what we would typically do. All right. But we will give you the punchline. And the punchline is that your intensity can be calculated to be your difference in pressure squared divided by 2 times the density of your fluid times the speed in the fluid. Okay? Now, how do humans measure sound intensity? We have found it convenient to measure sound intensity using what we call the decibel scale. Okay? And we denote the decibel level of a sound by the symbol beta. Okay? And so, actually, technically, this needs to be lowercase. Okay. And so we denote the decibel level of a sound to be, and this equation is essentially definitional, okay? This is not a derived equation. This is just an equation that we have found to be very useful. Okay, so I naught is what we call the reference intensity. Now, let's actually come back here for just a moment, okay? So if intensity is equal to pressure per area, okay, then this is going to be force per unit area per area. Okay. I'm sorry. Power, not pressure. I knew something was weird. Like, wait a minute. Yeah, power. My brain didn't work for a moment. So this is power is in watts. Okay, so the units on intensity are watts per square meter, or in other words, how much energy is being imparted to a given area per unit time. Okay, so this is energy per unit area per unit time. And that may be a more useful way of thinking about it. How much energy is being deposited somewhere in some unit of time over some given area. Okay. And in our case, for the human ear, the area is our eardrum, which is very, very small, right? So this reference intensity is, by definition, uh, equal to, let me rewrite this. Okay, so your reference intensity is given by 10 to the negative 12 watts per square meter. And this is essentially the smallest or lowest intensity that can be heard by the human ear. Okay, and so then I is the sound of your object. Whatever object you're measuring the intensity of, and you would measure the decibel level to be your intensity of the sound under consideration divided by this reference intensity. Take the log in base 10 of that and then multiply it by 10. Okay, so some common decibel levels. Okay, so if you're sitting in a office, for example, and you hear the music on the overhead in the background, it's usually fairly soft. 10 to the negative 7 is usually soft music. Okay. When you're talking with someone, like having coffee, coffee conversation, let's put it that way. Um, I'm sorry. This is your intensity level, and the decibel level of this corresponds to this. Your soft music would be about 50 decibels. Your coffee conversation would be about 60 decibels. Your let's say, oh, a machine truck, right? Like a semi truck or a concrete mixing truck or something of that nature. So if I have a loud truck, um, your intensity is going to be about 10 to the negative 3, and your decibel level, therefore, would be about 90 decibels. Okay. And by the way, 90 decibels is really about the threshold for damage from prolonged exposure. Okay. So if you have a history of really, really loud noises without ear protection at above 90 decibels, especially for extended periods at one time, like hours, then you're going to run the risk of hearing damage. Okay. Um, on the other hand, if I have a decibel level of about 110, okay, then if I listen to this for 30 minutes per day, then I can almost guarantee that there will be some damage. Okay, and this intensity is 10 to the negative 1. So if you go to a really, really loud rock concert, then that's about 120 decibels. And your eardrums will burst. At about 160 decibels. Okay. By the way, your rock concert is about 10 to the 2, and your eardrum bursting is an intensity of about 10 to the 4. Okay, so let's actually do a calculation. Let's do this loud truck calculation. So, and calculate the decibel level from that if we use the intensity of 10 to the negative 3. So, by the way, this is a beta, not a B. Really need to make that a little bit more apparent. Greek letter beta. Okay, so what is the decibel level if I is 10 to the negative 3rd? Okay, so our decibel level is going to be 10 times the log in base 10. And the reason we explicitly state this base 10 is because very often mathematicians and computer programs, if you just write log, they will interpret that as the natural log, right? But we want this to be the base 10 log. So that's why we explicitly put the base 10. And so then we're going to take this ratio of 10 to the negative 3rd divided by 10 to the negative 12. Okay. And so 10 to the negative 3rd divided by 10 to the negative 12 is 10 to the 9th. Okay. And 10 to the 9th, if I take the log of that, should be 9. And let's confirm. Sure enough. And so then 9 times 10 equals 90 decibels. Okay. So that is a quick example of using the decibel scale. Okay. So we will leave this lecture for the moment, and in the next lecture we will talk about standing waves in musical instruments and the Doppler effect. Okay. So stay tuned.